Greetings. In this video, I'm going to introduce chi-square tests as an example of nonparametric statistics. The tests we have learned so far, including t-tests and regression, are all part of parametric statistics because they require strong assumptions about the data. For example, t-tests are based on assumptions about the population parameters, including normality and homogeneity variance. These type of tests with strong underlying assumptions are called parametric tests. In some cases, the data we collect do not meet the underlying assumptions. What should we do? An alternative path is to use nonparametric tests, which have less restrictive assumptions than parametric tests. The chi-square test is an example of nonparametric statistics. Just to be clear, parametric statistics include hypothesis tests that require strong assumptions about the data, such as normality and equivariances. They are mostly used with large samples and quantitative measures. Examples of parametric tests include t-tests, ANOVA, and regression. Nonparametric tests are a family of statistical tests that do not make strong assumptions about the distribution or parameters. They are more appropriate when you have ordinal or ranked data, particularly from small samples that do not meet assumptions such as equivariances and normality. When the underlying assumptions are met, parametric tests are a better choice because they are more powerful than nonparametric tests. There are different types of chi-square tests. They are all based on the chi-square distribution. The chi-square distribution is a family of positively skewed distributions, each associated with a degrees of freedom. As the number of the degrees of freedom associated with chi-square increases, the respective sampling distribution approaches symmetry. The chi-square test is most frequently used in the analysis of nominal data. The first chi-square test I'm going to talk about is one-sample chi-square test called the chi-square goodness of fit test. It's used to test whether the observed frequencies of occurrence are consistent with some theoretical or expected frequencies. Let's start with an example. The chairperson of an organization's planning committee conjectures that membership preference for the upcoming national convention approximates the distribution on the left. She randomly selected a sample of 200 members, and their responses are shown in the column on the right. Using alpha equals 0.05, we test whether the two distributions are different. That is, we use the chi-square test to evaluate whether observed frequencies conform to the expected frequencies. When the observed frequencies fit the expected frequencies, the chi-square value is relatively small, indicating that the observed frequencies are within random fluctuation of the expected frequencies. So the null hypothesis is H0, the observed distribution does not differ significantly from the hypothesized distribution. And the alternative hypothesis HA is that the observed distribution does differ significantly from the hypothesized distribution. It's called the chi-square test because the sampling distribution is a chi-square distribution with degrees of freedom k minus 1, where k is the number of categories. With the chosen alpha level, the critical values and region of rejection can be determined. To calculate the observed chi-square value, the observed frequencies and the expected frequencies are compared. Their differences are called residuals. For each category, square the residual divided by its expected frequency and sum the ratios over all k categories to obtain the chi-square test value. In our example, the first category, Dallas, has an observed frequency of 20 and an expected frequency of 24. Their difference is -4. Squaring this value and dividing it by the expected value of 24 gives a ratio of 0.67. Repeat the same steps for the other categories and sum the ratios. The observed chi-square test value is 13.24, and the p-value associated with this chi-square test value is 0.039. With alpha equals 0.05 and the degrees freedom k-1 equals 6, we can look up the critical chi-square value from the table, either by comparing the p-value 0.039 with the alpha 0.05, or by comparing the observed chi-square test value 13.24 with the critical value 12.59. The null hypothesis is rejected. The conclusion is that given alpha equals 0.05, the member's preference for convention sites is significantly different from the expected distribution proposed by the program chair. Where are the differences? From the table, you can see that the largest residuals are with San Francisco and New York. There were 14 more than expected prefer the former, and 10 fewer prefer the latter. To run this one-sample chi-square test in SPSS, first open the raw data file, which contains 200 votes for the 7 categories of locations. The raw data are needed because SPSS does not provide an option to run the one-sample chi-square test using summary data in the format shown on the slides. I also created a numeric label for the locations so that they are numbered from 1 to 7. When the data are ready, go to Analyze, Non-Parametric Tests, Legacy Dialogues, and chi-square. Move location code to the test variable list. Since the expected values are not equal for all categories, enter the expected frequency for categories 1 through 7 in the correct order. Click OK when everything's ready. In the output, we have the observed N, expected N, and their differences in the first table. You can verify whether the information was entered correctly. The observed chi-square value, degrees of freedom, and the p-value are provided in the second table. They are consistent with the results of my hand calculations. Let's move on to the two-sample chi-square test. The two-sample chi-square test, commonly known as the chi-square test for independence, is used to investigate whether there is a statistical association between two categorical variables. Here is an example. A researcher is interested in the potential association between early exposure to learning and behaviors in the classroom. She conducted a study in which information was collected about children's preschool attendance and their behaviors in kindergarten. First, we state the hypotheses. The null hypothesis is that in the general population, there is no association between children's preschool background and behavior in kindergarten. The alternative hypothesis is that in the general population, there is a significant association between children's preschool background and behavior in kindergarten. We can use alpha equals 0.05. The formula to compute the chi-square test statistic appears the same as in the one-sample chi-square test, which shows the chi-square observed equals the summation of the ratios between the squared residual and the expected value of each category. But the expected values are calculated differently. I linked 3 videos here. One shows how to calculate the observed chi-square manually from summary data presented in tabulated format. And the other 2 show how to run the chi-square test of independence in SPSS, either from raw data or from tabulated data. For our example, the observed chi-square statistic is 11.50, which is greater than the chi-square critical value of 9.49 given alpha equals 0.05 and a degrees freedom 4. Also, the p-value from SPSS is 0.021, which is lower than the alpha value. We reject the null hypothesis and conclude that there is a significant association between children's preschool background and the behavior in kindergarten. Remember to check the residuals and evaluate which categories with large residuals contributed to the significant result. Also, be clear that chi-square test of independence only provides evidence whether 2 variables are associated. The magnitude of association need to be measured differently. But there are other types of chi-square tests that you will learn in more advanced statistical courses. But the 2 types we covered in this video are the most frequently used ones.